talking about the work energy theorem. And what I said here is that when a net force does work on a system, the work transforms the energy into other forms of energy by either increasing or decreasing the energy of the system. So my preferred way to actually write this conceptually is this way. And most of the time, this is the most useful way to write it for calculational purposes as well. Work is a transformative process, is what I said last time. And once this transformation process occurs, the system responds by either increasing or decreasing the total energy. So the work doesn't disappear, it just reappears as energy. So in essence, work and energy are really one coin, but two different sides of the coin. And my outline here is that I wanted to talk about, I want to track energy and energy by using a bar diagram. I want to look at how work depends on force and displacement and how you could do the same amount of work two different ways. We want to talk about the unit energy, the units of work and energy. And then finally, we want to get into the mathematics of the dot product and how it actually, what it actually means when we do this. So this is, let me just summarize what we did last time. And one of the things that we were talking about here is that we were talking about changes in energy in the system and bar diagrams. So what I did here is I defined the luggage as my system. And you could see that I used this light blue and defined that as my system. So what I'm going to be looking at is I'm going to be looking at energy flow either in or out of the system. And so as this person is lugging it, we want to look at the forces that are doing work. So I draw this free body diagram. So I have some force F that this person is pulling up at an angle. And then I break that force into components. And so now what I'm going to do here is that I want to know what are the forces doing work. And one of the things that we said here is that force can only be done if the force is parallel or anti-parallel. And perpendicular forces do no work. And we'll talk about that in a moment. So what we want to do here is that we need to identify what are the parallel and anti-parallel forces. So when I look at this thing, I'm going to start off, I'm going to do two cases. I'm going to start off with the case of constant velocity. Then I'm going to change mine to have acceleration. So let's look at this thing. So when I'm looking at this guy right here, what you're seeing here is that clearly when looking at the free body diagram and the direction of the displacement, the force F of X and D are pointed in the same direction. Because they're pointed in the same direction, that's positive work. So that means that this work is going to increase the energy of the system. So according to the work energy theorem, I start off with some initial energy. I now do work. That work then increases the energy of E2. So as a bar diagram, what I'm really seeing here is that I arbitrarily put the size of my block as almost 1 square. And then I looked at my work, well, that's positive, so it has to be some non-zero value above 0. And when I add both of these, you'll see that the total energy of the system had to increase. So picture-wise, here's my system of the luggage. And what you do here is that the work done by F of X flows into the system. And as it flows into the system, it's increasing the energy of the system. And that's what that bar diagram, and that's what that sort of like overall systemic view is looking like. So then I get to parallel forces. In this scenario here, anti-parallel forces, excuse me, the frictional force is opposite to the direction of the displacement. Therefore, the work is negative. If the work is negative, that means that the work of friction is decreasing the energy of the system. So when I look at the work energy part, the work energy theorem, you can see here that I have that important minus sign because it's negative work. But in a bar diagram, you could see that the work of friction is below. So if I start off at a higher energy, I go to a lower energy because work is taking energy out of the system. So picture-wise, I imagine that there's a flow of, right, work is being taken out. So it's essentially taking energy with it, decreasing the overall energy of the system. So that's what we were talking about right here. Now let's talk about perpendicular forces. Well, when I look at the work here, work can only be done if there is a displacement. But when I go to my free body diagram, let me bring this guy down here with me. What you're seeing here in this free body diagram, the displacement is along the horizontal direction. In this case, I can call that the x direction. Whereas in the y direction, there is no displacement. So what I'm really seeing here is that when I look, so what I'm seeing here is that I'm seeing that the normal force, that the force of y and the force of gravity are all perpendicular to the displacement. So what this is really telling me here is that delta x is not equal to 0, but delta y is equal to 0, because we're assuming that the suitcase stays on the ground. So when I'm looking at the work due to the normal force, I then would have the normal force times my displacement in the y direction, but that displacement in the y direction is 0, so therefore this must be 0. Then I can immediately say the same thing for these works. They must also be equal to 0. So these works do not contribute to changing the energy of the system. So since no work is done, the energy of the system does not change. So we've talked about parallel forces, anti-parallel forces, perpendicular forces. Now we want to talk about the total work done on the system. So let's go look at this guy right here. So when I look at this guy, what am I really seeing here? Well, we see that there are two different workings. So if I look at this picture-wise, I imagine here that I have the work of f of x, which is positive, and I have the work of friction, which is negative. So what this means here is that when I look at this picture-wise, here's what I see. Well, I have the energy of the system, and I'm going to arbitrarily make it this large. And I'm going to call this E1. So what's actually happening here? Well, there's the work of the force of friction. And what that does here, from what we've seen here, it does what? It pulls energy out. It reduces the available energy here. So this guy is doing this kind of work. However, the fact that the energy, because it's moving at constant velocity, is not changing, what I'm seeing here, let me make sure that I'm getting the right colors here, then this guy has to be equal and opposite due to the force of x. In other words, what this is really telling me here is that this guy is adding energy. This one's removing energy at the same rates, so that afterwards, the total energy of the system is unaffected. And the reason why this is unaffected here is because when I look at the network, right? So, oops. The network for an object moving at constant velocity is such that when I look at my free body diagram, we saw already that this was f of x, and we saw that this guy was f. And because we were moving at constant velocity, we know that these forces must all balance out. And because they all balance out, we could say then that the net work, which is equal to the net force times the displacement. And what you're seeing here is that in this case, this guy is exactly 0. And if the network is 0, then that means, as we already said, the energy entering the system is equal to the energy leaving the system. So if I go back and I get my suitcase, let me get the suitcase right here. Well, what am I actually seeing here? What I'm seeing here picture-wise is that I'm seeing that the rate of energy coming in, right? The rate of energy coming in due to the force F of x, the rate of energy coming in is equal to the rate of energy coming out. And as a consequence, that thing is 0. So that's what happens when you're moving at constant velocity. So the key thing here from the statement that we were talking about here is that it says this thing, that when I make a statement that the net work is 0, then the energy leaving versus the energy entering have to be exactly the same. Now, let's go to that case 2 here. So if I go to case 2, what we want to do here is that now we want to talk about an accelerating suitcase. And so what this tells us here is it says that if I am accelerating, then clearly the net force is not equal to 0. So therefore, the net work must not equal to 0. So if I look at this scenario here, what do I mean by that? Well, if we start off with the free body diagram of the system, then again, we assume here that the vertical motion of this thing is going to be fixed. And so if I look at the normal and mg and f of y component, those guys must balance. However, there must be an unbalanced situation between f of x and the friction, which tells us that, of course, we have acceleration. So when I look at the forces here, what we're seeing here is that the fact that the net force in the x direction is equal to f of x minus f, and that equals mass times acceleration, whereas the net force in the y direction, which of course looks like this, and this is 0 right here, what we're really seeing here is that when I look at the net work, the net force in the x direction for delta x plus the net force in the y direction, the change in the displacement in the y direction, since this has no change in the displacement, this whole term here is 0. But yet, this term is non-zero. So I can talk about accelerating systems if I have a net work that's greater than 0. So physically, what does this mean? So the question that I'm asking here is, physically, what does this mean? Well, if I look at this thing mathematically briefly, we could then say that the network then has to be what? It has to be the work done by the force F of x minus the work done by friction. And we know this has to be positive. So that implies here that there has to be an increase in the energy of the system. So I now have an increase. So picture-wise, what does this tell me? What it says here, using a bar diagram, so a bar diagram shows that f of x has to be greater than the work of friction. So imagine that I start off with the system. Let's say it looks this much. This is how much energy I'm starting off. Again, this is an arbitrary value. Now what I'm going to do here is that I know that the work of friction must be greater. So then I'm going to come up here and let's say that this guy is this amount. And this would be the force of F of x. And so when you're looking at this thing here, and I compare it to the work of friction, the work of friction must be smaller. It must be smaller. So what you're seeing here is that when these two workings, there is more energy being transferred into the system by the work done by F of x than is being taken out by the work of friction. So that the overall energy of the system must increase. So if the red is 3 squares and the violet is 2, that means that the overall energy of the system had to do what? It had to increase by 1. But the bottom line is is that energy 2 is now greater than energy 1. And so if I look at my system here with the suitcase, so if I'm looking at the suitcase here, right? If I'm looking at the suitcase, what I'm seeing with the suitcase is that when I look at this guy, that means that when I look at the energy flow, so the energy flow into the system, is going to be greater coming in than what is taken out of the system. So in this scenario here, you're finding here that more energy, here, let me take this out, move this up, more energy flows into the system. And in this case here, we have less energy flows out of the system. And so the power of this thing here is that what it's really telling us here is that when the work of f of x is greater than the work of friction, the increase in energy must, or does account for acceleration. So instead of talking about the word acceleration, we're just saying, hey, there's a increase in energy of the system. So in this case, it must be accelerating. So that's when it's accelerating. What happens when it's decelerating? So now what I'm seeing here is that if I have a decelerating suitcase, then that tells me that the acceleration is negative. If the acceleration is negative, that means that the net force must be negative. But if the net force is negative, then that tells me that the net work must be negative as well. So we know that this immediately means, just like over here, it told us that what this tells us here is that there has to be a decrease in the energy of the system. So picture-wise, what does this really mean here? Well, if I look at my free body diagram, the big difference here is it's what? That the frictional force has to be smaller than the force in the x direction. It has to be larger than the force in the x direction. And since my velocity is in this direction, we could see here is that the acceleration is then going to switch for, it's going to switch directions here. So again, what this tells us here is that then that the work of friction is then going to be, magnitude-wise, is going to be larger than the work of f of x. So it's pulling it out. So if I then do my bar diagram, it then says here. So if I have the energy of the system that looks like this, and this is the energy right here, then what I'm learning here is that according to this diagram, what I'm seeing here, well, the force of x does work in such a way that, let's say, it's 2 squares. So that's adding energy to the system. And that would be the work of f of x. However, the frictional force has to be larger. And therefore, it does more work here. So what that means here is that when I look at the energy, you could see here that the frictional force is 4 squares. The work of the force of f of x is 2 squares. So therefore, the net negative work is 2 squares. So that means it has to bring the energy down by 2 squares. So picture-wise, that's exactly what we would have expected here. And so what you're seeing here is that it's this difference right here, right? If I look at this difference, that is the change of energy. You know, I should have done the same thing up here, because if you look at this guy, that's the difference in the change of energy. That's a positive change. This is a negative change. So if I look at my suitcase scenario again, and I look at this from a systemic viewpoint, what am I seeing here? What I'm seeing here is that when I look at this thing here, of course, this is my system. And what I'm seeing here is that in this scenario, what happens? There is less energy flowing into the system, right? So in this scenario here, what we're saying here is that there is less energy flowing into the system. On the other hand, there is more energy flowing out of the system. So picture-wise, that's exactly what we would have expected right there.